Yeah, next up are algorithms for biclusters with constant values and in rows or columns. Yeah, so our second type of model, our first generalization to the basic model of constant values. Actually, there are different approaches how to do that. The most simple approach is a normalization to transform the biclusters into constant biclusters actually, and follow the first approach, for example, by Hartigan or variance. Other approaches try to do it application driven. Yeah, so they have specific assumptions about the clusters actually. Basically, these biclustering algorithms are extremely popular in the bioinformatics community. So these approaches somehow rely on special assumptions from the applications, so from bioinformatics, for example. Exactly. So other approaches could be for constant values in columns. For constant values in columns, exactly. We saw that they are somehow access parallel subspace clusters. So we could use, in general, access parallel subspace clustering algorithms or projected clustering algorithms for solving that problem. For constant values in rows, that is a special case of general correlation clustering algorithms that we will see next week. And in both cases are special cases, of course, of biclusters with coherent values, and we will have a look at algorithms for those. And that is actually the most, say, researched question, or how to compute biclusters with coherent values is a very, very deeply researched question, explored question. So, and we can, of course, see those different models as special cases, as we have discussed it before. So here are biclustering algorithms for coherent values, for biclusters with coherent values. They are also called pattern-based clustering algorithms. So these, as I told you before, biclusters with coherent values are very often called pattern-based algorithms. And there is a pioneering approach, I would say, by two authors, Cheng and Church, in 2000, already 20 years ago. And they introduced the term biclustering for the analysis of gene expression data, so again in the bioinformatics community. And also they realized that we have to introduce a kind of variance, bias, jitter into this basic model, where we cannot expect that there is really a perfect mean and a perfect adjustment in rows and columns. So they come up with a quality measure for biclusters, like probably the same as Hartigan here with this quality measure for the constant biclusters. Now for the model with rows and columns, and they termed it mean squared residue value. Term is H here, of a cluster defined by some rows and some columns here. And you see that this is actually the same as before. We take somehow the mean square error, sum it up, and normalize it by the number of values in the submatrix actually. Yeah? So we take the value and then try to compute how far it is from the average rows and columns, and from the average values in the whole thing actually. Yeah? And a submatrix then is considered to be a bicluster if its mean square residue is smaller than delta. Yeah? So if the average variation of the values in the submatrix from the expected from the mean of this submatrix actually is smaller than delta. Yeah? And for delta equals 0, of course, the whole thing is perfect, meaning that we have the perfect biclusters according to the original model of coherent values. Yeah? Okay, so how can we do that, or how can we compute that, or how can we use that to compute that actually? Well, the model for a perfect bicluster predicts a value by a row constant, a column constant, and an overall cluster constant. I mean, that is the basic cluster model. So the value can be computed by a mean a row bias or adjustment and a column adjustment. And well, if we take a closer look at that, the row adjustment is of course given by the adjustment of the values from the mean of the rows, or from the mean of the overall cluster, and the column the same, but with the rows. This one here, of course, is the constant basic value, the mu. Yeah, so we end up in having something like this here. Yeah, so in that case, each row and each column exhibits absolutely a consistent bias in the perfect in a perfect bicluster. Yeah, and then we can predict the value of each row and column in the submatrix by these terms here. Yeah. For a non-perfect bicluster, however, the prediction of the model deviates a little bit from the true value by probably some residue, yeah, by some bias here. We call it a residue here. So the whole thing comes down to, well, it's not a perfect prediction, but it's a prediction. It's the same prediction as before, but we have some error. We make some error here, and this error is quantified by this residue here. Yeah? And if we just reformulate this equation here, meaning that we just want to compute the residue by means of all the others, well, what do we have to do? Well, we have to bring these terms here to the other side of the equation. So we end up in residue is the value, the actual value, minus this plus the mu. Yeah, so we have the residue is the actual value minus the row mean, the column mean, minus the column mean plus the mean overall. Yeah, and if you look at this one here, that pretty much looks the same as here. So this is actually the optimization function, the optimization criterion that we had before. We want to minimize that here, yeah, that is exactly the justification that this residue is actually a good performance model. Yeah, because we want to minimize the error that we make. So this is the error that we make when we predict the actual observation from the cluster model actually. Yeah? So those three values here are actually part of the cluster model, because the mean and or the constant base value, so to say, and the row adaptation and the column adaptation depends on those three different things here, obviously. Yeah? So that is basically a good optimization function here. Yeah. So and then we try to Cheng and Church here try to optimize that by some optimization function, by some optimization algorithm. You can apply different things here, and there are somehow related algorithms that try to make it somehow better, because optimization algorithms always have the potential problem that they only find that they don't find the global optimum, but only a local optimum. So all the other methods that we just mentioned here are trying to optimize it in a little bit a different way. So here the P cluster algorithm specializes the delta B cluster property that we had here, this property here, to a pairwise property of two objects and two attributes. So that gives you a little bit of different pattern actually. Then there is an algorithm Flock that uses a randomized procedure, Maple, which introduces some improved pruning of candidates here, because you only want to have those that have a residue smaller than delta, and so on and so on. So here Koklos is something which tries out a kind of k-means-like approach for finding these different biclusters, and so on and so on. So there, as I said before, is a well-explored thing here. Yeah, so a short summary on this biclustering methods, and especially on the algorithms. So we have biclustering models that do not fit exactly into the spatial intuition behind subspaces, projected clusters, subspace clusters, or also correlation clusters that we will see next week, or get to know next week. So the models rather make sense in the view of a data matrix, and I mean, that's how they have been defined. So that makes sense, of course. Yeah. A strong point for those bi-clustering models is that the models generally do not rely on the locality assumption. Yeah. We don't care about any locality assumption in that case. However, be a little bit careful in selecting or also in interpreting different models, because the models differ substantially. Yeah, we have seen that here in this bigger picture here, that we have a couple of really so there is no specific categorization of these spatial patterns here of these different models. So what I just told you before, be very clear about what do you apply and what is the outcome, how to interpret the outcome, as always when you do unsupervised learning clustering in that case. Okay, so that was it, and next week we will talk about correlation clustering. Actually, Daniel will tell you something about correlation clustering, which is another big story, another big research field also, and we actually see us next, probably in 3 weeks, because this will take 2 weeks, correlation clustering. So in 3 weeks, when we talk about some different raw data representations, time series. Yeah, see you there, and as always, stay healthy so far.